So our next speaker is from Fetch Robotics, Michael, and he did lots of planning code in the movies previously, and now he's solving real problems like the warehouse. Let's welcome him.
Thank you. So I'm Mike Ferguson, CTO of Fetch Robotics. As was mentioned, I started as a software engineer, recently had to sort of actually stop coding. When you're a startup company, you can code for a while as the CTO and eventually they tell you to stop. So that we're just to that size now and sort of that point in building out this company. So we're in Silicon Valley. We were founded in August 2014, so we're just celebrating our second anniversary right now. Venture backed, we've raised $23 million to date. The last round being last year in about May, which was right around the same time that we actually announced what the heck we were doing. And so we've got about 40 people working on fetch and freight, right? So we're building robotic solutions for warehousing and logistics operations. It's come up a couple times today, people talking about the Materials Handling Institute, MHI. This past March at Modex, we were the Innovation Award winner for new solutions in warehousing. And so we built 2 robots, and I'll tell you in a moment what they do, but where we found robots to fit in, I'm going to talk about first. So we're going to talk a little bit about warehousing and logistics. And I think we've seen a bunch of different things about the use cases for robots and why this is important. I think most of the day today has been focused very much on picking, which is kind of the next thing coming up. I'm actually going to be talking a little bit more about transport because I can't talk too much about the picking operations that we're actually working on, but I can talk more about our transport side. And a lot of that comes down to the fact that when we sort of split out what people are doing and sort of where they see their time being spent, transport's kind of the big one to go after. That's also a now problem as opposed to a 20-year problem. So traditional solutions that people might be using are things like carts and forklifts. Obviously, you're putting a lot of people still in there, but you're letting them move around more than if they were trying to carry it all by themselves. You start to get into a lot of safety issues with forklifts. You can also then go to things like conveyor and automated storage and retrieval systems, which are really kind of like robots themselves, and in some cases like Kiva and Amazon Robotics, it's pretty much an ASRS in that you put stuff in and then you get stuff out, and the robots don't have rails that they're driving on, but you do have to configure the warehouse pretty closely for that type of operation. And so, Amazon obviously can afford this, but what about everybody else, right? Can you shut down your warehouse? Or I think in the case of Amazon, it's more that they're just building a new one. So let's update that one and make it this new thing and not worry about the old ones. But certainly if you are an existing warehousing operation, you probably can't tear your whole place apart, go in and spend a couple of months potentially bringing a new solution up. So you want things you can roll out incrementally. And you want things that can run alongside of your current stuff. I think earlier today there was some discussion about sort of human-robot interaction. We're definitely in that space, not so much at the point of like robots handing things to humans. That's a 20-year problem probably as well. But the robots working closely with people so that your people continue to work in the same space. And then the robots do, in this case, I'm going to talk a little bit more about the transport problem. So when you're done picking things, if you've got a lot of conveyor, you load stuff on a conveyor and it takes it away. But conveyor's not really flexible, right? You're going to install conveyor, it's going to be there for a very long time. It's not something where you can walk in and go, this really isn't serving our needs. Let's move it 10 feet over there. And so what we actually are primarily deploying at this point is our freight robots running around doing what we call a virtual conveyor, right? So we drop them in, and we have these different top hats for the robots that can be used for carrying stuff around, or you can put sensors on there and do surveys is another thing that a lot of people are interested in. But this is really the thing that is kind of the big one, because we can actually deploy this same day in a facility without actually integrating with your warehouse management system, right? And that's why there's a little screen on the robot. So we can go through and we can map out the whole facility, connect all the robots up to the Wi-Fi, get them connected to our central server, and then you can basically drop in and say, hey, these are the entry points to my conveyor and these are the exit points where I need things delivered. And it will deploy robots to those entry locations. People put stuff on and they select which of those exit locations the conveyor that they want it to go to. And so this allows you to then do things like move the conveyor with a click of a button. We do everything through web-based UIs, so you can sort of monitor robots, you can build the task for the robots, and you can tell them what they're doing. And so you really can go in, click on a button and say, you know, well, this used to be where my conveyor ended. I actually want it to end over here now. And now the next time somebody hits the button, maybe your pickers out in the warehouse don't even know that you've moved the shipping location on the other end. They just say, hey, go to shipping because that's where I want this robot to deliver this stuff. So that sounds really interesting, right? Really simple maybe. You know, hey, just robots driving around, right? Isn't navigation like solved, right? Didn't we say that like a decade ago, that navigation is a solved problem? So why am I even talking about this, right? Because there's still tons of challenges, and there's this big leap from, hey, we made it work once in a demo to, you know, sort of 99.9% plus a call center to deal with the fact that, you know, getting to that last, you know, that 99.99999 is really, really difficult to get to. And so I am going to talk about sort of some of the challenges that we've encountered and solved and whatnot. And I think actually most of the things that I'm going to hit on are actually applicable as well to the grasping and manipulation problems, right? Under the hood, actually, when we're doing arm planning versus planning for robots in spaces, it actually doesn't look that different as a planning problem. You know, yes, the dimensionality goes up. Some of the things that maybe were hacks that you could do in lower dimensionality don't work in the higher dimensionality. But for the most part, the same kind of things come up. And so certainly one of the big ones for us is, you know, scale and reliability, right? So this is a map of a 500,000 square foot facility, right? And everybody goes, oh, well, mapping, that's solved. There's two different packages in ROS. I'm actually the maintainer of one of them, right? You can use Slam Cardo, you can use Gmapping. Well, if you're a commercial entity, Gmapping is actually not licensed for commercial use, so you probably shouldn't do that. And if you use Slam Cardo, you're gonna find out that at about 25,000 square feet space, or just enough complexity, it starts to blow up, right? So this is like 20 times that size, and is extremely repetitive, which happens to be one of the things that kind of separates warehouses from probably your graduate student area where, you know, your robots are driving around and mapping these really nice buildings. Everybody can pick out like, oh yeah, that's the Intel building or whatnot, right? You know the building almost and know when you're comparing the different benchmarks. Here it's a warehouse, and I can show because you can't tell where that is. It's way too repetitive and bland. So scale and reliability are a big one. The other one I mentioned forklifts a little while ago. Forklifts are a really big problem. I've actually got two videos running here. I hope you can kind of see them, although they're maybe a little washed out. You know, the one is just kind of the 2D laser view, right? And then the other one is with 3D sensor view as well. And it still doesn't even look like all that much. This is actually, maybe you can tell, but maybe not. It's not actually a full forklift. This is a pallet jack, because they don't actually have any really nice videos of forklifts, and I don't actually have any in our facility either to record with. But forklifts, when we started getting into places, everybody tells you, oh yeah, no, we don't let forklifts in the area where the people are. You know, that'd be dangerous. You deploy the robot, and about 10 minutes later, you see a forklift go by, and you're like, what? So even you know, when you get into facilities, people don't actually know what's going on in their facility until somebody else, as an outside observer, comes in and looks at it. But certainly, you know, these are dynamic obstacles. Even just people moving around, right? If we're going to collaborate with people in the same space, they're a dynamic obstacle. And this is actually, one of the dynamic obstacles in general, the robot is also a dynamic obstacle now. So I'm also a maintainer on the open source navigation stack, which you can get on your research Fetch or Freight, right? And people are like, well, if this exists, then why are you guys building more software? Like, isn't that good enough? And one of the big things that the navigation stack, the open source version, does not handle at all is this dynamic planning problem, right? It assumes that everything it sees, yeah, it'll avoid that, but it assumes it's static, right? And so we've actually gone back, and as we've rebuilt our own internal navigation system, spent a huge amount of time on handling dynamic obstacles, right? And so this is actually a little view of what a robot looks like when you're not doing any sort of estimate versus when you actually are and you're filling it into the cost map here now and looking out. And when you start to add a forklift, suddenly the whole planning space is really taken up. And so if you're trying to just deal with dynamic obstacles as if they were static but bigger, you still run into issues, right? And so there's still a lot of work even in this area of dynamic. And this is just in 2D, right? When we go to 3D, it's going to even be worse. There are also sort of all of those non-robot pesky things that start to come in. And I think they've been mentioned a couple of times today, but it's certainly, the safety one I think has come up a couple of times, right? And I've heard a couple of people say as well, why isn't this in the field yet? And actually, I think this is definitely one of the biggest ones in many ways. Is that there's safety standards for a robot arm in a cage. There's really nice safety standards for AGVs. You put an arm on an AGV and nobody knows what the heck's going on. There's actually a brand new NCRIA safety committee that I recently attended the meeting for, and that's going to be one of those things where your early adopters will be okay with it, but as you start to get into bigger industry, right, they're going to want that problem to be worked out. They don't like gray area, right, and that's definitely a legal gray area. Wireless connectivity, as soon as we start going mobile, maybe not so much for a picking robot if it's staying stationary and you're bringing stuff to it, but if it's moving around, this is actually an area where we've spent significant effort, right, beyond just building out, the robot capabilities. It's that wireless part. And then integration is this other part, and as we talk about, not telling you what the objects are until right then, right, that's kind of that same integration problem, right? Figuring out how data gets shared among the organizations, and as it turns out, when you start to deal with big WMS systems, they've got a lot of data in them and nobody's really sure what all the data is sometimes, right? And so trying to get things into representations that the robots will understand is going to be a really big challenge as well. And so those are kind of the challenges that I was planning to hit on, and I think sort of some of those takeaways can be really applied as well to the 3D space. And so yeah, that's kind of my wrap up on sort of the mobile part. Certainly we are working on mobile manipulation, but I can't go into a lot of details on that. So, and I guess I'm going to back up for just 1 second because I did forget to say sort of at the beginning there. When we're looking at it here, I probably should have given a little bit more description. I thought I had another slide in there to actually talk about the robots more. But yeah, so we have Fetch and Freight, right? And so we are a little bit similar to a video you might have seen a little while ago. Transport separated from picking is I think a really good idea. And so the freight robots are definitely rolling out in commercial operations right now. Fetches will be shortly. Is definitely our plan. And I think you probably already saw a video earlier today there of a Fetch being used in a research operation. We do also have that research version of the robots available, which is, I think, pretty interesting in that compared to something like the PR2, where they were built purely for research. They have a certain level of robustness. These guys are actually being deployed into the field, and coming back to that sort of reliability and robustness side, we're not quite at that 150 million miles, but I think we're at like a couple percentage of that already, even with like a small number of robots so far out there. And you know, you can't buy a Kiva robot for your lab, but you can actually get a freight. So, yeah.
Thank you. So what about end effectors, if you can talk that, or do you see a lot of...
Yeah, so I can actually say, so end effectors are, I don't think there's going to be just one that works for everything, right? I think you've definitely seen a lot of that. We do actually use, the end effector is actually a point of modularity. So you can pull that end effector off. It uses the same ISO standard as like the UR5, right? And I think that kind of standardization, seeing more of that across more vendors and across even things that people build in their lab could be very, very helpful. Because even though you might not be using the same robot as somebody else in, say, the Amazon Picking Challenge, if everybody agrees on the same standard of how the gripper interfaces, right, and I believe you can get the Moto Man, the smaller arms, the UR5, our robot, all have the exact same mechanical spec. The ISO standard 9409 does not actually cover the electrical part, so that's still a challenge in that I think it's a CAN bus is available in the Moto Man. I'm not actually sure what's available on the UR5, and we've gone with Ethernet to make sure you can put cameras and whatnot out at the end effector, because I think that's also, as you're going into boxes and things along those lines, you're going to need sensors out at the gripper.
Yeah, that was the other question, because in terms of sensing, we see...
Yes, yeah, so this is, I like to call this the 80% gripper, right? So for about 80% of the random tasks that researchers want to do, that gripper works great, right? Internally, we have a number of other grippers that just aren't actually available. They're kind of all in R&D at the moment. But this is sort of the simple parallel jaw, gets the job done. The newer versions actually have an Ethernet hub actually right inside of the gripper, so you can add, you know, Ethernet-based force torque sensors or cameras, etc.
I thought the APC says that vacuum does 8%.
I guess for that particular one, we do actually have a self-contained vacuum gripper, but it's never quite made it into a full-on product yet. So, yeah.
So how many mobile robots with LiDAR, right? The sensor?
Yeah, so each of the robots has a LiDAR sensor in the base.
Right.
And then this is actually a slightly older photo. It doesn't actually have the, but I really like this photo, but it doesn't have the camera visible there in the base.
So how many LiDAR equipped mobile robots have been worked together in the same space with each LiDAR looking at the other one and not interfering?
Yeah, so we have about 20 robots in a test facility that we have. Can't actually go into numbers that are in individual warehouses as well. We're cramming them into a tight space to find those kind of issues, and certainly there is interaction between lasers and cameras and things along those lines. And that's one of the things that we work pretty closely with our vendors on those sort of things. Actually, the SICK laser that is in here is the 25-meter TIM, which was a brand new model that we work, in some respects, we work with SICK, along with other customers as well, to develop what we wanted, because the 10-meter offerings were not going to work that well in warehousing facilities.
So they do interfere with each other when they are...
You can get, there are modes of interaction in which there is interference, and we've certainly worked around it in software. My hope is that in the future, there'll be hardware solutions as well that are more robust than our software solutions.
Also, about the speed, so when the mobile robot moves at a high speed, in pretty large range of the LiDAR, do you have a ratio of how many, so what's that detect range of the LiDAR versus the speed of the mobile robot?
Well, so the LiDAR will go out to 25 meters. I think it's guaranteed something like 10 meters on that 90% reflective white. But that's a lot further than, that's 5 seconds of the robot at max speed. And we tend to not quite run it full on max speed, because again with the interacting with people, even though the robot won't actually hit you at the 2 meters per second, they're just not comfortable around it above like 1.4, 1.5 until you're around the robots enough that you become comfortable with it, right?
So 5 times is pretty much enough for navigation.
I would say so, but I mean there is, if you're interested in something along those lines, the technical standard 15066, which is sort of the co-robot safety standard that's still evolving. It's not actually a fully accepted standard, but that one does have what they consider safe for speed and separation distance, which I think is, it's done differently and it's way more mathematical, but that's kind of the evolving standard for that kind of an area potentially.
Thank you.
The Amazon Kiva robot, they put QR code on the warehouse floor. Why do you feel that you don't want to like follow that solution, also put QR code there?
Well, one of the other parts about that is that they're the only thing driving around on that floor, right? And so they've got a lot better control. You put a forklift drives across one of your QR codes and wrecks it, you're going to have a bad day. You know, the other part is that I'm pretty sure those QR codes get laid out when there's nothing in the warehouse, so you can kind of align it properly. To ask people to sort of take everything out for even a day is just not going to happen, is our opinion. You know, that's kind of the market we're going after is, hey, you can incrementally roll them out, right? And as our feature set improves, right? So as we get closer to Fetch being available, and you know, for potentially, you know, a small subset of objects initially, right? You can incrementally add to your fleet and shift where your labor concerns are.
Is there any failure mode at what time this robot will break?
Is there any what?
Failure mode, failure cases.
Well, I think if you've built any system, you're going to have some failure cases. I mean, there's certainly things that we've listed as just completely out of scope. You'll notice there's no drop sensors. There's no, like, nothing safety ready to say, don't go down the stairs. That's, you know, one of the things where rather than trying to build that into every robot, right, that's part of your site analysis and the risk assessment of the facility, is that you specifically say, hey, this is out of scope.
Also, one last question. So if we have like, say, 100 robots running the same warehouse and they all share the same map and with the same global planner, somehow they come up with the same path, right? And then they all jam together.
Yeah, so we did, I mean, while the robots are independently autonomous and can carry out right onboard planning, they're definitely getting some higher level commands from up above. I don't think you can sort of independently guess what every other robot's going to do in any sort of reasonable fashion when you get that many out there.
But if you do like centralized planning, path planning, then like it won't scale, right? Like if it scales to like 1,000 robots, then the centralized computing just didn't work. Like in real time, because like the other, if there's something comes in, right, another robot comes in, or another robot just break down, or there's like some dynamic obstacle in front of you, the whole plan needs to be recalculated.
Yeah, I mean, scale is definitely one of the challenges of things.
Right. So anything that you can share on that line?
Not really. No, I can tell. We've definitely looked into things along those lines. We've definitely done work in that. Yeah, but I can't really go into how we're solving some of those things.
But if you have a centralized planner, you can just make sure they don't go together.
Yeah, but like, so it will happen. Something will happen is like if there's dynamic obstacle or if something breaks down, you need to recalculate the whole plan. And then if there's more than 1,000 robots, it didn't work.
And there is another workshop on multi-agent path
Right.
planning that
Yeah.
discusses that.
Yeah, I mean, there are some things out there. You know, I think there's actually a number of sort of things in the patent space around that as well that might be a little bit more advanced than what's in the you know, even the research papers.
Are there any other questions, Dinesh?
So, you know, one of the advantages in the morning, one big talk has been perception and, you know, integration of pattern planning. So one of the experiences that we are facing, talking in my talk about robot working next to humans, you know, predicting human action. I would say more flexibility, and if I can design a sensors, more cameras, move them around dynamically. Do you ever see that coming up, because I think we need more flexible architecture where we can change the perception capabilities. I feel that need from more and more applications.
Yeah, I think modularity is modularity of what you're installing is definitely a big request. I think it becomes a real challenge as putting on my hardware provider hat, right? That becomes a really big challenge in the design aspects because cabling is actually one of probably the most difficult parts of, high dimensional, high degree of freedom robots is that, as you're building out the cabling, every extra cable you add in that has to go through a joint, definitely reduces the life or increases the size, or maybe a little bit of both. And so, yeah, I think more modularity would be great. I think there's something to be said for sort of trying to design, rapidly prototyping things before you try and build the full, the fully robust and life expectant version of those.
Definitely, Mike.